email from Dr. Long.
Yeah.
Yeah, so I've been able to do it.
Yay.
I
That makes me happy.
emailed her back yesterday.
Cool.
So the tentative dates, for
So there's two we're guaranteeing, which is February during X period and April during X period. The March, I think it's the 15th one, has been confirmed. I just need to, I've got to finish doing it.
Okay.
It's in the evening, and we're gonna have a 2-hour thing. And then the other two, I can't confirm the February one until next week, probably at the earliest.
Okay.
It'll probably depend upon COVID numbers because I know it's the 25th, and so we've got 2 weeks. But basically, it all depends upon the COVID numbers and if NCTR will allow us to have people in.
Okay. I was just wondering like how close to like how tentative those were.
So basically, the March 15th one is done. The other two are still tentative because I gotta wait until I get a little closer to the time frame to look to check with the company to see if they're gonna let me bring people in.
Okay, but if it does happen, it will happen probably on that.
Yes.
Okay.
The dates are set if it does happen.
Okay.
It's just I don't know if it'll happen yet.
I gotcha.
Or if it'll have to be pushed off to next year. That's one thing about this mentorship circle. It is actually ongoing, so it'll be going for the next year too. And next year, one of the things I'm hoping to do is take students down to Denton for like a graduate school tour as one of our trips, if you will, for the mentorship circle, and then some maybe go over to nuclear one, something like that. So we've already been, so right now we've already been to down in South Arkansas to a plant that manufactures the weaponry, the bombs, basically smart bombs and stuff like that. We've already been to there. This year and then if we can pull it off, we'll go 2 places this semester next. So there's 1 trip at least each semester, sometimes 2.
That's really
This
cool.
one is 2 because it's in town. But one of the goals behind all these trips is to actually get what you can do with a chemical degree besides go to med school or pharmacy school, or what are your options? Because there are lots of options, obviously. So anyhow, so yeah.
Do you have class right now?
I do. It starts in a couple of minutes.
Okay.
Nope. Stop chewing on that. Show them this. You want to say hi? So big. Oh, you're getting so big. Yes, you are. Such a good girl. You got somebody said, hi, Luna. schedule?
Where's my schedule?
You're a bear. I'm not a bear. What are you doing? What are you doing? Are you getting into mischief? You getting into some more mischief? Make sweet little bit. Oh, you're a good girl. No. No. Oh, up you go.
I know, I keep picking you up and putting you down.
What are you grumbling about? What are you grumbling about? I don't know. Yeah, my lab's not big enough, is it? Getting to be a big. Okay, you ready to get down? Down, ready? Oh, no, no, ma'am. No, ma'am. No, ma'am. No. No, 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 no. Got angry at me. Okay, folks, it is that time of the day, so we are going to go ahead and get started. There's your Chem 101 code 9426. Study sessions. So the one that is in the middle of today from 2 to 3:30 has been canceled. I will be leaving campus at 1:30. But there is a Zoom session. It will be using the exact same link as you're using for class. And it will be from 7:30 to 9 p.m. tonight. That way you can get in last minute questions before the exam tomorrow. So that's what we'll be using our lab time for tomorrow is exam number 1. The other things to just make note of, Sunday you have homework 3 due. Homework 3 will be over speed of light calculations, energy calculations, and quantum numbers. With respect to quantum numbers, one of the things I always do is I always look into where we are by the end of the week. So on Friday after class, I always try to go and look and see how we gone over everything that's in that homework. And if not, I'll edit the homework on Friday so that you're not having to do questions that you have not been introduced to. Also on Sunday, you have 4 math, chemistry, and puzzles that are due. They are found in last week's folder. Now, as I've mentioned previously, 2 of these are related to stuff that is on exam number 1. The other 2 are related to the stuff that we're doing currently and that will be in the lab next week. Today, I plan to finish up the Rydberg-Balmer equation calculations and go on to Bohr model and then finally get into quantum numbers. And I am super excited about quantum numbers. Basically, what we're going to just
talk about is the fact that the periodic table, I've mentioned before that it's not haphazardly arranged. In fact, the periodic table is arranged based on quantum numbers. It's arranged, and so we can actually figure out a lot of things using the periodic table with respect to quantum numbers. And so I feel like when we get into quantum numbers, we're really going to be getting into understanding what an atom of an element truly looks like, which to me is the coolest part. So on Wednesday, the last thing we did is we started with this equation, visible light of 434 nanometers is emitted. What energy level did the electron fall from? And what is the energy associated with this transition? And so we made our list of information we were given, which was 434 nanometers. And because we were talking about energy levels, that's the reason that I use the Rydberg-Balmer equation, because it has energy levels directly related to it. And therefore I needed the R value, which is the Rydberg constant of 1.097 times 10 to the minus 2 per nanometer. And then I needed N sub F, and N sub F came from the fact that we had visible light. That is telling me what N sub F needed to be. And that is 2. So anytime you get visible spectrum, anytime you get the visible spectrum, it is going to be N sub F will equal 2. And then we started solving the Rydberg equation. I tried to rewrite it so it's even cleaner looking than it was on Wednesday. But basically the first thing I did is I plugged in all of my information, then I simplified the fractions. Then I divided both sides by the Rydberg constant. After I divided both sides by the Rydberg constant, I then subtracted 0.25 from both sides, which gave me a negative number on the left-hand side is equal to negative 1 over n sub I squared. I multiplied the entire thing through by a negative 1 to get rid of that negative. So we have 0.03966 is equal to 1 over n sub I squared. And then I took the inverse of that. You can do so by 1 over the number, or you can just use your inverse key on your calculator, which is x to the minus 1. That gave me 25 is equal to n sub I squared. And then you take the square root of both sides to get the n sub I. Now that number, n sub I, should come out to be a quantized number or a whole number. If the Rydberg-Balmer equation works for an element, that number will be a whole number. But here's the thing. The Rydberg-Balmer equation, this particular equation, only works for single electron systems. So it only works for hydrogen, helium plus, or lithium 2 plus. It only works for systems that have only one electron. Now, we need to answer the other part of this question, which asked us, okay, what's the energy associated with this transition? And there's actually going to be 2 ways to calculate energy, but one of them is going to be a better method. And the one that is a better method is going to be to use this equation, which we'll come back to. Before I do that, though, I do want to talk briefly about this diagram that I started to do. I want to basically make sure you understand what it is we're describing when we say n sub 5 and n sub 2 and all of that jazz. So right now, what I want to do is I want to describe what is meant. So in an element in its standard state, whoopsies. An element in its standard state has the electron in the lowest level. Now, when you excite an atom or an electron, what you're doing is you're exposing that electron to some form of energy. That electron then is going to jump to a higher level. In this case, it jumped to N of 5. Now, you cannot see the excitation. I mean, yes, there are instruments that we can use to get the excitation energy, but you cannot see it per se. Now, when this electron has been excited to the 5th level, so now our electron is in an excited state. Because the electron is not where it belongs. Atoms of elements, their electrons cannot remain in the excited state. So they are going to relax. And as they relax, they give off energy. And that is the energy that you are seeing. That is why it's called an atomic emission spectra. Now, yes, this electron will continue to relax and it'll eventually come back to level 1. But what we observed when we were talking about the Rydberg-Balmer equation is that the electron relaxed from energy level 5 to energy level 2, and that is when it gave off the 434 nanometers of light in the visible spectrum. Any questions about this? This is conceptually what you determined with this Rydberg-Balmer equation. This Rydberg-Balmer equation conceptually means this. Now, again, that second part of the question asked us to calculate the energy. We can do it 2 different ways, but I will say that using the energy equation where delta E is equal to negative 2.18 times 10 to the negative 18 joules times Z squared over N sub F squared minus Z squared over N sub I squared is probably the better way to do this, because it's going to help us to determine the sign associated with the energy and what it all means. So let's get into this. So our delta E is what we want to calculate. Our Z is going to equal 1 because Z is the atomic number which is 1 for hydrogen. Our N sub F, we said was equal to 2 because of visible light. And our N sub I, we calculated as 5. So our delta E is going to equal a negative 2.18 times 10 to the minus 18 joules times 1 squared over 2 squared minus 1 squared over 5 squared. Keying this into the calculator, you get a negative 4.78 times 10 to the minus 19 joules. Now, the reason I like this particular equation is because it tells us the sign associated with our energy and what the sign means when we're talking about energy. If it is positive, it would mean energy is absorbed. If it is negative, it means that the energy was given off. So basically what this is saying is 4.78 times 10 to the minus 19 joules of energy was given off as the electron relaxed from energy level 5 to energy level 2. That's what it means. Energy, by the way, folks, is not negative. That is something you need to know. Energy is not negative. The sign is just telling you whether it is absorbed or whether it's given off. That's all it's telling you. It itself cannot be negative. Energy is always positive. Kind of think of yourself. Can you have negative energy? No, you can have zero energy, but you can't go into the negatives. Energy can't be negative. The sign is only telling us whether it is absorbed or whether it is given off. And in this case, it was given off, just like this little drawing showed up here. As it relaxed from energy level 5 to energy level 2, the wavelength of energy was given off. Now,
So when we
technically,
type in our answer, we don't put the negative. We just put the answer.
So on Chem 101, it's going to ask for, it all depends on how it's worded.
Okay.
If it just asks for the energy change, you better put the negative.
Okay.
Just like mine, it was what is the energy associated with it? It's negative because it is losing energy.
Mm-hmm.
But if it says how much energy was emitted, then I would have left it off. So it's all in
Okay.
that terminology. Folks, if you would have used this other equation, you would have gotten the exact same answer, but it would not have given you the sign. Numerically, it would have been identical, but it would not have given you the sign. Okay, so let's look at one more example of this before we go on. What is the energy required to excite an electron from Ns2 to Ns5 in a helium plus ion? So because I'm saying excite here, what do you think the sign will be?
Positive.
It's going to be positive. Okay, so let's get into this calculation. Our delta E is equal to a negative 2.18 times 10 to the minus 18 joules times 1 over n sub, or excuse me, z squared over n sub f squared minus z squared over n sub I squared. In this particular case, because we are dealing with helium, helium has atomic number of 2. So Z is equal to 2. Now, N sub F is where it goes to. It goes to 5. N sub I is where it starts from, which is 2. So our delta E is going to equal a negative 2.18 times 10 to the minus 18 joules times 2 squared over 5 squared minus 2 squared over 2 squared. When you key this into the calculator, you get a delta E of 1.83 times 10 to the negative 18 joules. And note, the prediction of a positive was correct. Okay, any questions about that? Notice with this one, you had to use this particular equation. You had to use this equation because we didn't know wavelength. So you had to use this one. Okay, so we've talked about the photoelectric effect. And we said with the photoelectric effect, an electron had to have the correct frequency, hence the correct energy to excite it so that it would completely leave the atom. That energy is the energy needed to overcome all proton-electron attractions. And now we have discussed the atomic emission spectra, which results from the electron transitions between quantized energy levels. So Niels Bohr developed what he calls the Bohr model of an atom, of an element. And technically, this is the Bohr model of hydrogen. So I'm going to do two pieces. I'm going to talk about the photoelectric effect with the Bohr model, and then I'm going to talk separately about the atomic emission spectra. Okay, so if we're dealing with hydrogen, we have one electron in its ground state. It is going to be in that first shell right up against the nucleus. With the photoelectric effect, we have to put in the incident beam needs the correct frequency. Hence energy. To overcome all attractions. Right now, this electron is attracted to the nucleus. You have to put in enough energy for that electron to overcome all attractions, so it'll be completely kicked out of the atom. Now, if we're talking about it as the atomic emission spectra, I'm going to put this as a different electron, just, even though it's still hydrogen, so pretend this other one doesn't exist now. For the atomic emission spectra, we don't overcome all of the all of this attraction. We still have attraction here, folks, but we're not going to overcome all of it. We're just going to excite it to a higher level. Whether that is to the 6, to the 5, to the 4, to the 3, or what. We're just going to excite it to a higher level, so we don't have to overcome all of that proton-electron attraction. But with the atomic emission spectra, what you are observing when you see visible light is that the electron, once it's excited, is going to relax back down. Now, it's not, while I've drawn it as a single atom here, keep in mind, when you add electricity to a hydrogen lamp, you're going to excite a bunch of atoms at the same time. So you're going to see all of their emissions at the same time. Whoops, that should have gone all the way to 2. I missed one. Going to see all of their emissions at the same time because you've got multiple atoms being excited at the same time. So basically, Niels Bohr developed this model where there's quantized levels, and the electron had to be in one of those levels. It can't be halfway between. It had to be in a level. And this model, Bohr's model, explains hydrogen just fine. But it doesn't explain every atom. Doesn't explain every atom out there. So, folks, the next piece of this, you do not have to write out unless it will help you. I'm going to go over some of the science that actually took us to where we understand the atom of the element and where the electrons reside, not just for hydrogen, but for every element out there. So the photoelectric effect, the atomic emission spectra, these observations, along with some others, led to an understanding that electrons have a wave-particle duality. The wave is the light. So for instance, purple light, that would be the wave. The particle is the electron and where it is in the quantized levels. That's the particle portion. So we have a wave-particle duality. When Bohr developed his model, he considered this duality paradox. And he said that this dual nature, this wave-particle dual nature of an electron are complementary to one another. Well, that makes sense because the particle relaxed from a higher energy level to a lower energy level, and the wave of light was given off. We have both at the same time. Another scientist by the name of Heisenberg, he developed what's called the Heisenberg uncertainty principle. But basically, he considered the question further, this wave-particle duality of an electron, he considered it further. And he saw the duality as present in all entities, but he did see it slightly different than Bohr did. But basically, these theories of Bohr and Heisenberg, along with the observations like the photoelectric effect and atomic emission spectra, led an individual by the name of Schrodinger. Yes, the same individual that's responsible for Schrodinger's cat, led Schrodinger to develop a quantum mechanical model that basically described the address, if you were to think of it kind of like a regular address, describe the address of an electron. And basically the equation is the Hamiltonian operator times the wave function is equal to the energy times the wave function. Now, the Hamiltonian operator times the wave function expands using calculus to this equation. And folks, this is just for hydrogen, the simplest of all atoms. When you start getting into multi-electron systems, it gets a lot more complicated very, very fast. Now, I'm not expecting you to solve calculus. I'm expecting us to understand what came out of the calculus. If you are a chemistry major and you take physical chemistry, you will get to this. But for now, we're just going to look at what came out of the Schrodinger equation. I'm not going to have you solve it. And now this is where you do need to start picking up with taking notes. The Schrodinger equation produced 3 quantum numbers, and these quantum numbers are kind of like an address. If you think about your physical address, you have the state you live in, you have the street you live on, and then you have your house number. For the electrons in an atom, these quantum numbers basically describe the state they live in, the street they live on, and their physical address, the house number. Now, the first of these quantum numbers you've actually already seen. Bohr just didn't call it the same thing as Schrodinger did. And that is the principal quantum number. The principal quantum number is represented with a lowercase n. It will always be a whole quantized number, starting with 1. So 1, 2, 3, 4, 5, 6, 7. Now, the principal quantum number, yes, we can call it the principal quantum number, but you'll also hear it called as the energy level or the shell. I will use the term shell quite a bit. And the shell indicates how far away from the nucleus an electron resides. So basically, you can think of this principal quantum number. Let's think of an onion. You have the very center of the onion. The first layer would be in, that center of the onion would represent our nucleus. The first layer of onion around that center would be the shell 1. It's the first shell around it. Then you have the second, then you have the third, then you have the fourth, then you have the fifth. And each time you add a layer of onion, the size of the onion grows. With principal quantum numbers, you have the 1 right up against the nucleus, then the 2, then the 3. And so as we add shells onto our atom, the size of the atom is going to grow. Meaning if you get an electron in the principal quantum number 6, shell number 6, we're talking 6 layers out from the nucleus. That concept of the principal quantum number and how far away from the nucleus the electron resides is going to be very important in understanding atomic size, understanding atomic reactivity, and various other aspects. The second quantum number is called the angular momentum quantum number. It is represented with a cursive. It's really just a lowercase l, but so that we can distinguish an L from a 1, it's typically written with a cursive L. And the angular momentum number can be any value from 0 to n-1. So in other words, the smallest value it can be is 0. And then it can go up from there for an L value. Where it goes to is dependent upon where we start with our number. Or where the principal quantum number is. Now, the angular momentum quantum number is often referred to as the subshell. And the subshell describes the shape of the orbital where the electron most likely resides. I keep saying most likely resides because the fact is the Schrodinger equation simply describes the probability of finding an electron. So where it most likely resides. Now there are 4 that we currently know. When your L equals 0, the subshell is referred to as an S subshell, and it's simply a sphere shape. When your L is equal to 1, it is called a P subshell, and we call this one a dumbbell shape. When L comes out equal to 2, it is referred to as a D orbital or D subshell, and we call it a cloverleaf shape. And when L is equal to 3, it is an F orbital. And I don't have a name for it. Now, in this particular diagram, what you are seeing is distinct shapes, meaning that you can definitely see the outline here of the orbital or the outline of this one. But in reality, that the distinct shape is not exactly correct. What the Schrodinger equation does is it develops an electron density map. Basically, it predicts the density of where the electron is. And if you look at the shape that the Schrodinger equation, well, if you look at the shape that the Schrodinger equation predicts, or the density that it predicts, you can see the outline where the majority of the electrons are. And that's what it's describing when we say it's a cloverleaf. And so a lot of times, yes, we'll draw it where it looks just like a filled in, not cloverleaf, a filled in dumbbell. But in reality, it's not quite that. It's the closer to the nucleus the electron can get, you will notice the higher the density. The further away from the nucleus, the less dense it is. Now, the third quantum number is the magnetic quantum number, which is represented with an M sub L. And the magnetic quantum number can be anything from a negative L to a plus L on a number line. So in other words, if you have a 0, 1, 2, -1, -2, It can be, you have to go both directions on the number line. And what the magnetic quantum number is specifically describing is the number of orbitals. What I've just given you are definitions. It's going to take us through, probably even through Monday, to start to really take all these definitions and hopefully get to understand what they mean. They're just definitions right now. So for a valid set of quantum numbers, it has to follow the rules. Meaning your n has to be a number from 1 to 2, 3, 4. It has to be a quantized number. Your L has to be something from 0 to n minus 1 for that n value. And your M sub L has to be a negative L to a plus L for that L value. So let's just start by building up a couple of the first ones. So let's say we have an n of 1. Then our L can be anything from a 0 to 1 minus 1, which is equal to 0. So our L only has the option of 0. Our M sub L can be anything from a negative L, negative 0, to a plus 0. So it's still 0. So what this means is that we have a 1, where the electron is in the first shell. S subshell. And there is only one orbital. Because there's only one value for the M sub L. Okay, so let's look at the next possibility where L is equal to 2. And our M sub L, our L, where N is equal to 2. That means our L can be anything from 0 to 2 minus 1, which is equal to 1. So our L can be a 0 or it can be a 1. Now for our first one, let's take our 0 our M sub L for this one can be a -0 to a +0, so it's still 0. For the other L value, it can be a -1 to a +1. So it can be a -1 all the way to a +1. So we have the choice of a -1, a 0, or a 1. So in the second shell, what does it mean? There is an S subshell. Because L is equal to 0. And it has one orbital. Because only one value of M sub L. It also means that in that same one, there is a P subshell. Because L is equal to 1. And in the P subshell, there are 3 orbitals. Because there are 3 values of M sub L. Questions? This looks like a good place to start. Where we will pick up on Friday is we're actually, if I were to continue this, I could continue it for quite some time. But I'll pick up with this diagram on Friday, and then I'll actually talk about what these M sub Ls mean. I will see you then.